straight, but where do we see a line?
On the graph.
So graphically, we see a line,
Yeah.
right?
Tablically, we see constant additive.
Okay, so on a table or tabularly,
Oh,
right?
tabular. Okay.
Yep. We see a constant additive.
Rate of change.
There we go.
ROC.
All right, additive rate of change, right? So we're adding the same on the left and the right. By the way, what's that constant additive rate of change called? It's called a.
Multiplication. Wait, hold on.
It is shown as multiplication, but it's called a.
Effect. A constant factor.
Say again.
What'd you say?
Remember, we just said constant additive, didn't we, guys? What's
Yeah,
that constant
constant
additive rate of change called?
Slope?
What?
Hey guys, can you guys pause? You're shouting out words, but pause and listen. A factor. What do you do with factors? So a factor is something you multiply by, but we just said we're constantly adding.
So multiplying.
Constant additive, but what's the name of it? Okay, let me ask this. What's the equation for a linear function?
Y equals MX.
Say it again, Taj. What's that constant additive rate of change called? Slope. Remember, we multiply by slope because multiplying by x shows that constant repeated addition, but we don't use the term factor there because it's not a constant factor. So remember, use those different forms to help remind you of these things. Literally, when you look at a line, what's one of the first things you're programmed to look for in that line?
A line.
What about that line?
See,
The y-intercept. What's the second thing?
see if it's adding.
What?
If it's a line, you already know it's adding.
Right.
Right divided by right.
And what is that called again?
Yes, sir.
The slope, right? Remember, when we talk about a linear constant additive rate of change, you look for the what in that line?
Slope.
Slope. It's not to trick you or anything like that. I'm doing this review because, guys, you got to demonstrate understanding today. You need to focus on these things.
Oh, wait, whoa, huh? You said demonstrate your understanding?
I said it was supposed to be Friday, and then we didn't finish what we were supposed to. There's no questions to one
I
what.
wasn't here Friday, so like, where?
You mean the demonstrate understanding that we were supposed to do Friday that we didn't get to because I was giving students more time to learn, so you should already have been ready? That one?
No, I thought y'all did it Friday.
You watched the video though, didn't you?
No. I told you to block me on YouTube. Right
Oh, I blocked you on YouTube.
Okay,
Okay.
actually, because
I'll give you this, you're funny, but that's not true. Okay, so, we were supposed to do a demonstrated understanding on Friday.
Yeah.
We didn't get to it because we're doing it today.
Wait,
So we're
is this
doing
on-
it today.
Is this on quadratic?
There is a note about quadratics, yeah?
Oh, okay.
Okay, but linear, as a graph, it's a line, constant additive rate of change in tables. That constant additive rate of change is called the
Slope.
slope, right? Y equals mx plus b. But we move that into the exponential function. This marker is dying.
It's going out, not down.
Nope, it's dying. Exponential. What do we remember?
Exponential curve.
Okay, so we need to recognize or look for those exponential
It's
curves.
also constant multiplying.
Constant,
Multiplicative.
multiplicative.
Also the
Rate of change.
equation,
Rate of change.
y equals a times bx.
Hold on one second.
Whoa.
What's that constant multiplicative rate of change called? A constant factor, right?
Yes, sir.
Now we see it. Where do we see that constant factor, by the way? That rate of change is in a
Table.
table. So remember, different different representations reveal different features. And what's the equation?
Y equals a times bx. It's
To the x.
The
Oh,
exponent
raised to
top.
the x?
Yes, to the x.
Okay. Why does it need to be raised to the x?
Because it's exponent.
Because it's an exponent, yes, but also because what is that exponent, variable exponent showing? Repeated what? Multiplication, right? Remember, it's not random, these equations. They are literally based on what that function is doing.
Yes.
Okay? Literally based on what that function is doing. All right. Does that answer our questions about relations versus functions as a whole, linear versus exponential? Was that your question? Go ahead. Okay. All right. So we're going to do a quick wrap up on samesies. So this is going to help some of you who did not do what they're supposed to do, study for the demonstrated understanding. Oh yeah, who's back? I don't know. Okay. Then we're going to do a demonstrate understanding on identifying the three types of functions and if a relation even is a function. And then we're going to move into a Desmos activity. So we're going to start with a Mathematician Monday, and so that demonstrate understanding afterwards. All right, so Dr. Erica Tatiana Camacho, I think is how you pronounce that name. I realized the other day that I had failed as someone trying to celebrate diversity in mathematics, that I have yet to do a female mathematician, and there's tons of them throughout the US, the world in general. And so Dr. Erica Tatiana Camacho has a very interesting story that I want to celebrate, and I hope it somewhat inspires you because, again, I don't care where your background is, you can be successful. And she has some details in her life where it should challenge you to think about, yes, the one.
Which one is her?
The taller one here.
Oh, okay, okay.
If I remember correctly, I think that's her mom.
Alright.
But she was born in 1935, so a hot minute ago, right? Nearly 90 years ago at this point, in Guadalajara, Mexico. And so in being born there, not a ton of money for her family. Her dad actually died when she was 3 months old, so her mom was raising her completely on her own and struggling. And so her mom actually taught to her grandmother. Dr. Camacho and her 3 older siblings actually went and lived with their grandmother for a while. While living with their grandmother actually had them going out and selling candy and selling all sorts of other things, like, and not like in a kind way, in a way to make money off of her grandchildren.
Oh.
The money that her mom sent to support her children, the grandmother never really put forward to them. They actually still grew up hungry because their grandmother was just looking out for themselves, or for herself. And so eventually the mom caught on and took her children back, but she was still struggling. She actually somehow, which I didn't get this part of the story, but she met someone who lived near LA. They ended up getting engaged and then moving to the US. This was late elementary school, early middle school, I think late elementary school. And so when they first moved, right, they're coming straight from Mexico, not any English, if I remember correctly, when they moved. And so the first 2 years or so was living in an area where there's nobody speaking Spanish. Brother actually got stabbed within the first week because they were chased. I can't remember if it was it was just a group of young men who were being prejudiced and racist towards Mexicans. And so chased after him. It was actually chasing after the entire family, and the brother tried to stop them and got stabbed. So, pretty rough life. Ended up moving to East LA with the family in 7th grade. And so this is one of the details from the story that really hit me. She was mistakenly placed in an honors English class. This is someone who's been in the US for a year or two, does not have much English whatsoever, and got mistakenly placed in honors English. And so she was supposed to be in an SEL, or ESL, not SEL, ESL, English as a second language class, to help her develop her understanding of English. And I don't know if the guidance counselors just didn't care or what, but she was not able to actually get into that class after like a week or so. And so the teacher just said, hey, look, listen, I know, I can tell you care. If you come in during lunch, if you come in after school, and you work hard and work with me, I'm going to make sure that you learn and get where you need to be. After that 7th grade year, she only took honors English from there on out. Because she worked hard, and she learned, and she grew through that experience. This is one of those times where I just have to point out, like, for real, hard work pays off. And the hard work of that teacher, the hard work of her trying to improve her situation, paid off huge. Where she took an honors English, and shouldn't have even been in a regular English class, was supposed to be in an ESL class. Tyler, how did a phone just go off if you don't have a phone on you?
Oh, God.
So, the hard work pays off, and that's something huge there. Apparently there was a movie called Stand and Deliver. It was in 1988, and it was all about this guy named Jamie Escalante from Bolivia. He moved to the US, and he was a high school math teacher, and legitimately loved his students and just constantly challenged them to be more, and had Saturday morning math tutoring sessions or math sessions to help his students overcome. And it's what spurred several people to go on to places like MIT and Harvard and things like that. He regularly had those alumni, those previous students. Tyler, just go ahead and leave the second phone up if you have to. Thank you, sir. So he ended up having an alumni come back from MIT and talk to Dr. Camacho's class. Before this situation, right, like she's already gotten into these honors English classes, she's already being successful, but in this class, he had someone from MIT come back and talk about the beauty of engineering and how he was applying mathematics and the kinds of job offers that he was looking at and the kind of car he was driving, things like that. And she went from saying, hey, all I want to be is a store clerk, like that was her dream at that point in time, to being in this man's class and seeing what hard work can do and can pay off. She decided she wanted to be an engineer. Like that, and made that choice and started working for that. Started working hard for that. And she actually ended up deciding not to do engineering. She went on to earn a PhD in mathematics, dealing with racism, dealing with prejudice all the way through, even in her very first situation as a college professor. But she has made such a difference because she worked hard in elementary school, or middle school. She worked hard in high school to overcome those issues and learn honors in English and math. Now she studies mathematical physiology, which is one of those things where she realized, what is that sound? How do we not hear? Yeah. There it goes. All right. What she does is she studies blindness. Most of the times when we think about blindness, we think about medicine, we think about biology, we think about all those different things. And so what I need us to recognize in this situation is she saw mathematics as a different way to approach that. And so she found a beautiful way to say, hey, I wonder if there's a mathematical structure underlying these things. And so she started exploring that. And she was the very first to ever look at, hey, how does mathematics play into the biological component of this? And so the challenge I want to ask you and I want to extend to you is, what difference are you going to make? What difference are you going to make in your academic life? What difference are you going to make in your future? What difference are you going to make in the world around you? Because all of you can do that. As a young girl, all she wanted to do was be a store clerk. That was the most she thought she was capable of. But through working with teachers, through hard work, she's overcome that, gone way past what she thought that she was limited by, and has now become a college professor in mathematics. She didn't let her backstory, she didn't let her background define her, and it wasn't until high school that she started to see mathematics differently. That's where you are right now. So, what difference are you going to make? That's the challenge I want to extend to you based on Dr. Camacho. So, thanks for listening to that Mathematician Monday. But let's...
Which one was her?
Say again? The taller one. Yeah. I think that was her mom. I have to go back and look at the... Huh? Yeah, so like her mom, so I think this is Dr. Camacho and this is her mom. It was her mom who was not taking care of her children. And that's why she took her kids back. So again, like, overcome those challenges. I'm here to support you in that. Your other teachers are. Yes, Cameron.
You said she was born in 1935.
Yeah.
Still alive.
That is not what she looks like now.
Oh,
And remember I said she's almost 90 at this point.
Still alive though, right?
Huh?
Still alive.
Yes.
Okay.
you know what happened to her brother? Did her brother die?
No, he did not die. He survived.
Good.
Alright. So, remember we're all about identifying functions first, if a relation even is a function, identifying the type of mathematical representations, And what we are finishing up or doing demonstrating understanding on today is this piece here of identifying if a relation is linear, exponential, quadratic, or none of these. And so we're going to base this on this samesies activity that we had on Wednesday. Wednesday? On Friday? Today's Monday. I don't know what I'm doing. I'm struggling. All right. So if you could get out samesies for me. We tore this out last Thursday.
What is the same?
It's what we worked on Friday. We tore it out on Thursday.
I wasn't
It
here
was like
Friday.
that. You weren't here Thursday or Friday? It's what we worked on Friday. Yeah. But did you not get the sheets out?
Most the work the same as we had on Friday.
No.
You said you gonna print something.
And I never did.
Mr. Kenny, Mr. Kenny,
Hold up.
can you print one?
Me too.
Holy crap, guys. And first off, have y'all even looked, Taj and J Mike? Like, we tore these out on Thursday. Huh? Have you looked in your notebook to see if you got it? Because we tore it out on Thursday. Then you don't need me to print a copy.
He didn't
Oh,
know
J Mike.
that was me.
That was Jim Mike.
That was me and Jim Mike.
Just, so I need 3 copies of this? Alright, I'm not putting the cards in there, I'm just gonna do the other part.
What y'all, you said Thursday?
Hey. I said, hey.
To look at these relations together, and so we first, if you remember, sorted out what was not a function, what were linear, what were exponential. We're going to focus on quadratics for a little bit before we do a demonstrating understanding. Yeah. Huh?
He got a
He
white.
has a white.
He has a white.
Yeah, I'm married. Been married for a hot minute now. We got a 2-year-old son at this point. Yeah. What's up? Okay. All right. So we should have our cards still. Should have written down what was not a function.
Took a picture of it.
I don't know about none of this.
It's right, yeah.
Okay.
Took that picture.
So here are. Hey guys. Regardless.
Oh, yeah, we show.
Hey, we should be able to M1 dash something. That's
Got
like.
it like on Wednesday.
Oh, well, I still.
It's M1.
Thank you. M1 dash 31 is where we should be looking. This is all your old. What's the stuff that we tore out last Thursday? Oh my gosh. All right.
I don't know nothing about no pages. I got these.
And I'm home. You leave.
Yeah, that's right.
I don't know.
But what
Those
page
who
you talking
needed it,
about?
printed copies. Huh? Yeah. All right, right here. Let's talk about these 3. Why did we label these 3 as not a function?
Because they're not a function.
Thank you for that circular logic of they're not a function because they're not a function. It's right up, well, what did you have?
Oh, I was talking about X. I was gonna say what I did.
Oh, this.
Okay, we'll talk about that in a second. J Mike and whoever else and Kamaya. The pages you need are right there. You just need 2, there's sets of 2. Say again. All right, so Makaria, X, tell us about it.
Okay, so what we did for X was we tried to put it in the tried to put the information in the graph, and it came up looking like the it came up looking like that.
For this one?
Yeah.
What do you mean? How did you put it in a graph? Like you graphed it by hand?
No, we like on the calculator.
How did you graph that on the calculator?
They table graph.
Yeah. And I don't remember. I can't remember. But I just don't have to.
Okay. I mean, you can make that work. I would point this out. First off, why is this not a function?
Good.
It's multiple inputs going to.
Yeah, one input is mapping to
Multiple outputs.
multiple outputs, right? I like that. Not even just 2, right? It's multiple. It's more than 1. Why do we know, so not a function, why do we know this table and this graph are equivalent?
Because.
And I will say they are equivalent.
Yeah.
It's all.
Oh,
Ask-
X. The
Yeah.
ones that are not a function, they're equivalent.
Yeah.
I don't even know what to tell you.
So what you
So what you
say?
say?
Oh, actually, walk like 0, and if you look on the right, that 2. Wait, look, I'll show you.
Sure.
Wrong answer.
Come on, like. I put like
I see what you got back.
see, so it's zero too, right? Zero right there. Is it two?
Oh.
See that? See next to see it's like right on that line.
That's way smart.
Is that right?
Okay? Now, let's be careful. Excuse me. Eyes and ears, because we gotta learn this.
Yes, sir.
What is this point again?
0 and 2.
Where's the next intercept?
It's
So-
minus. Yeah, X.
The x is what?
X.
The x
I mean,
is
2.
2. What's the y?
0.
So is that the same as this right here?
Yeah.
Not at all.
No.
Not at all.
You just told me x is what? What is the x here?
Zero.
So are those the same?
No.
No.
Tweak it.
We gotta be careful with our points. Remember, 0 in the x means I'm not moving left or right. 2 in the y means I am moving.
Oh.
So it is that point.
Right.
0, -2 is this point.
Yes, sir.
Gotcha.
1 in the x, 1.73 in the y. -1 in the x, 1.73 in the y, and -1.73 in the y.
Yeah.
Notice, how do I know that that table and that graph are equivalent?
When you look at it, and you see that the fact that the points are
The points what?
The,
I don't want to use that word add, the points what?
they're equivalent.
What?
What are you talking about, boy?
Okay, that makes it a function. Hey guys, what does it mean to be equivalent? Like, these are things that you've got to know.
The
No,
same.
they are the same, so are
Oh.
those the same?
They tell the same story. They're two different mathematical representations that tell the same story.
Good job.
Nice language, I love it, right? Notice, look, at the end of the day, the same inputs map to the same outputs. Guys, those points are clearly on this graph.
Yeah.
So the same input is mapping to the same
Output.
output. That's why they're equivalent. It's the same language I've used from the beginning. If they're equivalent, the same inputs map to the same
Output.
outputs. What about this? How would I know?
It's 2x. It's exponent.
It's got 2 squares on it, which I'll point out, it's got 2 squares, so it's not quadratic.
Then
Yeah,
then
only
they
have
don't
one
on
every point,
exponential
right?
neither.
If it's just on the x. Well, yeah, technically, if it was just on one. Say
Then
again.
they exponential either because the x ain't in the exponent.
Nice note on that, right? There's no variable in the exponent, so it's not exponential. But I will point this out, is this equivalent to O and X?
Yes.
Yes.
I wouldn't know unless I graphed it on a calculator, or remember, the same inputs map to the same.
Output.
So is 0 squared plus 2 squared equal to 4? Notice that's my x and that's my y.
Yes.
What's 0 plus 4?
Four.
Forward.
So do they map?
Yes.
Very much so, right? So are they equivalent?
Yeah.
Yes. Right? Now you can check all the points, and they do all need to have the same inputs mapping to the same outputs. All right. First off, any questions about why this is not a function,
No.
and why they are equivalent?
No.
You need to understand these things. You need that language component to it. Identifying not functions, yeah.
I got a question.
By the way, is it still a relation?
What?
Yeah.
Why?
O and X.
It's a mapping between
Input, output.
inputs and outputs, right? It's a mapping of inputs to outputs, so it's a relation.
I got a question. So
Go for it.
if I'm gonna demonstrate your understanding, right, and I get my answer wrong, but I still got a whole bunch of understanding on there. I get that right?
Now, just writing stuff is not the same as having understanding.
Right, what if I-
But if you show me understanding and then just get the final answer wrong, that's still a lot of understanding. That's where that DE plus and even a CE comes from, right?
It's really not just based on.
Who said they got help up in here?
Yes.
He tell you that just in a
Okay,
smart
so
way. Just in a smart way.
don't let it be.
I'm just saying.
So, yeah,
Show that we try, we still get an
no. You have to show me understanding. Now, if you're actively trying, are you going to understand?
Who's that?
No, she be
You're trying more recently, but you don't always try, so it affects your understanding.
Jim, what you doing?
All right, linear. These are the 4 linear ones that we looked at. So if you want to write this down or note that these were the 4 linears. Go for it. All right. Say again.
Good notion where you have to like.
All right. So, Demaya, why is this linear right here? Because what?
Straight, I can't say straight line.
I mean, you just don't need to call it a straight line. A line, by definition, is what?
Linear.
Yes,
A straight
but
line.
it
A
is
line
straight.
is a straight
By
line.
definition, it is straight.
Right.
It's linear. Okay.
But we can still say.
So is this linear? No, just call it a line.
Okay.
It's linear. It's a line.
Yes, sir.
Okay.
I do.
So,
I mean, G.
why is G linear?
Because you can put
I need other people.
it,
The formula.
Oh, slow. Wait,
Slope.
what were we talking
And,
about?
What is my slope then?
I want to do.
M.
M, which is
2x.
Now, be careful. It's not 2x. It is just 2. But how do we know that? What's up?
you can put it in the calculator. Like,
Okay. So could I just put it in the calculator and graph it?
Yes.
Yes. However, do be aware, for full evidence of understanding, I want to see that you can look at an equation and know.
Okay.
So justify it based on that. So how could I justify this based on the equation?
See,
You
2x.
see the X.
And you think about
the
it.
M. Think about the M.
Okay, so identifying m as 2. Also, by the way, what's happening between this 2 and the x?
The 2 is the M.
Multiply.
Multiplied. Oh yeah, Cameron, multiplication is repeated what? And so if it's got a constant additive rate of change, we got that simple multiplication in there. That is strong evidence.
Yes, sir.
How do we know C is linear?
Because 2, 4, 6, 8, 10 is that about 2.
Is that true?
That plus the adjective.
Okay.
Yep.
Constant additive rate of change.
Yes, Lord.
And when I look at this verbal, right? But each day 2 new people hear about the secret, so it's repeatedly what?
Adding.
Adding by 2. Hey guys, I want y'all to notice, like, this is what we need to do when identifying the type of relations. I get it that it's different, and we struggled a little bit. Hey, right here. I know we struggled a little bit with it on Friday, but all you have to do is look for that rate of change. These are all linear. Now, I do want to point out, are these all equivalent?
No.
Sure about that?
Yes. No, I'm not sure.
What's my constant additive rate of change here? 2. If I substitute 2 in, what's 2 times 2?
4.
Wait, so the same input's mapping to the same output?
Oh my God.
If I substitute a 4 in, what's 2 times 4?
That's 8.
Oh, so same input mapping to the same output?
Oh, that's crazy.
Now look here. Isn't that the point 1, 2?
Yeah, pretty much.
Is this, not pretty much. The answer is yes. 3, 6. Are those the same inputs mapping to the same outputs?
Yes, sir.
So are they equivalent?
Yes, sir.
Okay. Brady, you with me?
So the
Everybody zone it out.
inputs match to the same outputs, right?
Same inputs are mapping to the same outputs. Same thing here. On the first day, how many people knew? 2 people. So on day 1, how many people knew? 2 people. So are these equivalent?
Yes.
Notice all 4 of the linear are telling the same story from different perspectives. That's it. Those are equivalent relations. And they're specifically, they're all linear.
I think they're
Functions. Exponential. How do we know these are exponential? What do we see over here in this graph?
Exponential curve.
Notice that language, right? This is an exponential curve. Oh, so it's exponential.
And I
That's
see
it.
it. And I see it multiplicative
Where do you see multiplicative?
on that table.
On the table? Multiplying by what?
2.
And then I want to point this out. Multiplying by 2 can keep going, right?
Yeah.
How many times can I multiply by 2?
A lot. Needed.
As many times as needed so it can change?
Yes.
So it can be x times?
Yes.
So we get 2 raised to the x, right? And the same thing is true over here. So what would I say about all of these exponential functions?
They're equivalent.
They are equivalent.
True.
They're equivalent. Now, for the sake of time, we need to go through the quadratics together. So if you have your cards with you, I would look at these quadratics. This is what we should have finished up on Friday. We should have noted these things on Friday. So first off, Chelsea, how do I know that A here is a quadratic? Okay.
Wait, what you said? Oh, the parabola.
Huh?
The concave
The parabola.
down.
Concave
The
down,
parabola.
Like a
Parabola?
frown.
okay? So we got a concave down parabola, we got a vertex, and so, by the way, like, this is quadratic because it's,
Did you just make it go?
Parabola. This quadratic because of parabola.
it's quadratic because the graph is a
Parabola.
parabola. That's it.
You know what I'm talking about? Another
Okay.
thing.
So Chelsea, you good with that? All right.
It's bent down.
Now, the goal was to identify which quadratics are equivalent to this, correct?
Yes.
Okay? So, first off, I want you to look at this equation. It's time to learn. This is what time it is. What? It's time to learn. That's what it's time it is. So,
Can I say why?
pause. Stop John had to do the least. All right. Right here. F. Jamie, why do we know F is quadratic?
Because of the thing, it's the same as the, like, almost where you got the linear function, linear thing, times something like that, you know what I mean?
In F?
Yes, because you got the,
Oh, I know.
slope intercept form.
Okay, so, hey, chill. Listen. Hey, guys.
Yeah.
Hey, I hear a lot of talking that.
Why?
This is my class or not yours?
Oh, bro,
Chill.
you gotta go.
Okay,
Quiet.
right here.
Oh, tree, you thought it was the main character.
Hey, Jamie, Mike. So, there is a linear component to this, but Jamie, you're talking about linear being multiplied, right? But what's happening right here? That's not multiplying, that's what?
I just said it.
It's what?
I said it's the slope intercept form, because it got the,
But Jamie, that's my point is that's not what's making it quadratic.
Call on somebody else, I don't care. You don't have to call on somebody
You
else.
thought he was finna get
Hold up. You can't get upset because I'm trying to help you understand it better.
Upset, but like, that's the same thing you showed us last week, and I'm telling you what it is.
Alright, so tell me more.
I just told you.
So I'm missing something. Tell me what you're talking about. I don't disagree that that's slope intercept right there. What was the other part of what you were saying?
What's the little X thing? They rise to the second power.
Oh, because originally you were talking about multiplying linear. That's what you originally said, and that's what I was trying to caution you on. You may have gotten there eventually, but I want us to be careful that we're not multiplying linear right here. That's just what I wanted to emphasize. But do we have a square here?
Yes.
So that's what makes it quadratic. So you're right on that part. Just be careful with your language, because we're not multiplying two linear, right? That has a square that is making it quadratic. Now, I hear what's happening in I, because I don't see an x squared this time.
It's the same.
It's the same thing with multiple.
There's two x's, so it's basically be x to the second power, right?
Gee, why you so loud?
I get x
Trying to
squared.
get some going points.
But this is what Jamie was referring to originally. This is what? X plus 3.
No, it's better.
Okay. Yeah, but what type of function would x plus 3 be? That'd be linear, wouldn't
Oh,
it?
yeah.
Y equals mx plus b?
Yeah.
This piece is
Same.
also linear then? And if I take a linear times a linear, I get a quadratic.
Quadratic.
Yes, it'll be a square, but the idea is that if I have a linear function or linear expression times a linear expression, it's going to make it quadratic. And so we have these other features. Now, I have all of these grouped because they are what? Any guesses?
Equivalent.
If I graph -4, -1,
Oh,
-3, 0, -2, -1, -1, -4, and 0, -9, do all those points map?
I'm pretty sure.
Pretty sure, right? I see them on the graph, don't I?
Yep.
Yes.
Okay? Graphic or algebraically, how do I know they map? Well, we're going to go into those forms of quadratics after the demonstrated understanding today, so you can start to see why those are the same. And we're going to use a Desmos activity for that. But really quickly, I want to point this out, and I need y'all to pay attention to this, because this is what defines a quadratic, but what most students struggle the most with. We didn't talk about this earlier.
No.
We can see a graph pretty easily. We can see an equation.
Pretty.
How, looking at this table, could I have known it was quadratic?
That's I would.
the fact that it's wonky like that.
You're wonky, but no.
Oh,
No.
I try to answer the question.
I know, I'm sorry, that was playing too much. Alright, look, guys, what did we look at in both linear and exponential when we had a table? We looked at the what?
Constant rate of change, right?
But we don't have a constant additive rate of change. If it was linear, we'd have a constant additive rate of change.
Yes.
But should I still look at the rate of change?
Yes.
So what's happening to go from -1 to 0?
Add,
Adding how much?
What?
0 to -1?
subtract it. Subtract the 3.
So notice we're getting more negative, so we're subtracting.
So I would
Five.
be simple enough.
So notice that's not constant additive.
Not at all.
But -2, -2, -2. This is what? Constant additive. And what type of function had a constant additive rate of change? A linear, right? Now, linear function, but this isn't a function, right? This is constant additive. This set of differences is linear, but we are adding. And so it's a linear additive.
Rate of change.
That's what made it quadratic, and it's equivalent to the rest. So don't forget, when it comes to a table, if it has a linear additive rate of change, it is quadratic.
Okay.
Notice B here. How do we know this one's quadratic?
It has x to the second power.
X squared, right?
You said that too, it could be quadratic, right?
If it is
Where
x
he said if it ain't.
B, how do we know it's quadratic?
He said if it ain't.
Hey, chill.
Parabola.
The parabola. Now, look at the table.
3, 5.
You know it better.
So, definitely not constant additive, but this is, if this is constant.
Yay.
Now, we'll tear these pages out to start tomorrow. This is lesson 4 from the textbook. And so you'll notice from the textbook, they give us these 3 forms there, and they just expect you to be able to list different key characteristics. Does anyone, or what, not does anyone, what do you remember about these 3 equations here?
Or no.
I mean, are they quadratic?
Yes.
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 Definitely quadratic, but what else do we know? Like if I gave you this equation, could you graph it?
Yes.
Wait.
Possibly, I mean, those are numbers. Those are numbers.
Right, but if I gave you one in that form, if I told you y equals 3 times x minus 2 squared plus 4, do you know anything about that quadratic to be able to graph it?
Yeah.
Yeah.
What do you know about it, Makari?
It's raised to the second power.
It's what?
Raised to the second power.
Yeah, but like how's that going to help us graph it? Like there's actual specific things. Now that's going to tell us it's a parabola, right? But we got to know more than just that. So usually this is the case where we don't know those features. And so when we talk about these equations from the textbook, A, B, and C, A, R1, R2, A, H, and K, think about that like M, your slope, and B, your y-intercept. They're unknowns right now, but they're just values on the equation, or values that we connect to the graph. And so, I need you to go to student.desmos.com and type in this code. And we're just barely going to get started with this, but it's going to help us be set up for tomorrow. So, student.desmos.com. I would have my iPad tomorrow, for sure, because if you log into this once, you will always have access to it in the future. So, log in. Are you excited? You good?
What's that guy at?
You want me to just try to change that something?
No, log in, dude. You have an account. Guys, y'all should have accounts. Log in with your accounts. We created those when we did log in with Desmos, I think. We used our TCSS email address.
Did we do
Did you hit
that?
Google or Desmos? Sign in, log in with Desmos. You made it, but more than likely, I suggested that you use your TCSS email and password. That was what I recommended at least.
So logging with this.
No.
God, no.
Yes. Sorry.
Two.
Yes.
That is a good question.
94.
Can't tell
I
me
know you
how to say
here.
it.
You here every day, you ain't supposed to.
I'll just wait a second. Okay? Yeah.
What car the wheel?
Look
It's the
on.
wheel that like the wheel.
Little with the ones that can't.
Little who?
Here you go, guys.
Okay.
I thought you were my friend.
Ready? Did you need me? 94, 48.
I thought you were.
Capitalize it?
Yeah.
All right,
Please,
ladies and gentlemen,
yes, sir.
eyes and ears here. One, I do want to say this. We got to study.
Let's go.
We got to do check your understanding questions. Because those demonstrate understanding questions, identifying what type of function, one, is all throughout the check your understanding that I gave you. Literally, I had a different section on the check your understanding for graphs versus equations versus tables.
Yeah.
For the mild, the medium, the spicy. We got to be able to recognize those things. And so we'll go over it tomorrow. But right now, we got to start getting into quadratic equations. So when we talked about linear, we had y equals mx plus b, where m was my slope, and what was b again?
Y intercept.
The y-intercept, right? There's a point slope form of the equation of a line, and there's even there's a standard form.
Yeah.
And so each of those values represents something specific. Well, today we are going into the vertex, standard, and factored form of a quadratic to find out how those things affect the parabola. And so we don't need to get up because we don't have a ton of time, but I want you to just note, pay attention to the directions at the top. Because they're going to tell you exactly what to do. You adjust the value of a in standard form of a quadratic function and observe what happens to the parabola. Move to the next slide when you have a conjecture about how a affects the parabola. The reason why you only have one iPad is because I want you to talk. And so I want you to all be looking at the same iPad, and I want you discussing what A does. So let's work with each other. Let's play around with A a little bit. And let's try to come up with a conjecture of what A does. While she's trying to figure that out, do it on my laptop. Adjust it. You guys, what are you doing? What are you doing?
Oh, doesn't have something I can't have one did.
Come on.
Which one I put that?
Slide one of these.
Man, that was him.
Slide two, sorry. Deanna, you looking on what John looking at? Hey, can you give that card for me?
That was vertex.
That's what we figured out what's going on here? Why did you make B that large? How did you make B that large?
I just did. I thought
That moved vertex crazy. So it all moved vertex. Yo, stop. Man.
She's a dog, you can't.
But it moves the vertex, there's some good language. Anyone notice anything else it's doing? Okay, it's changing the direction. Okay, what direction are you referring to there?
Side direction.
Excuse me, Big Daddy.
Oh, see, I wouldn't have gone with that. It does. Wait, the what? The up like a cup versus... So notice A right now, is it positive or negative?
Positive.
A is positive, it's concave. Watch what happens when it becomes negative.
Concave down.
Concave down. So tomorrow we're going to pick up with this, but hold on to this little nugget that A is determining that concavity.
Oh no, it's I was like, look at my. I heard it down.